So we have this thing in Vertex form, right? Which again is just the one that we're used to, right? We're giving it a new name because we can look at it and identify where the vertex is by using the stuff we know about transformation. What is the vertex here? 2, -3. Okay. Important to keep in mind, and we'll talk about this a few more times as we go, but the vertex is a point, right? It's a coordinate pair. It's an X and a Y. So it's an ordered pair. Where the vertex occurs, generally, if we say something like that, we mean the X value. What is the maximum or minimum value? Meaning what is the highest or lowest the function gets? That would be the Y value, right? So that'd be important in applications where, if we're trying to answer a question like, what's the maximum number of people who did a thing? Well, the answer to that is, a number, 6 or 1,000 or whatever it is. It's not an ordered pair, but the vertex is the thing that tells us about it. What's the axis of symmetry? It's a line, because we're talking about functions, a vertical line that runs through the vertex. So this one would be x equals 2. Some stuff about what these things are, right? Okay, what's the domain? Yep. One of them we'll talk about, again, this some more over the next couple of weeks, but quadratics are a type of polynomial function. Linear functions that you've done, previously in other classes, that's another type of polynomial. One of the reasons we like polynomials is because they're always defined everywhere. So they're a very sort of nice or friendly or, easy to get along with sort of a class of function. They're defined everywhere. What about the range? -infinity to 3. -3. Why -infinity to -3? Okay, so -3 is important for sure because it's the vertex, right? So at 2, -3, there's a point on this graph where it's, changing directions. How do we know it's opening down, Lisa? It's got the negative out in front, right? Again, think transformation stuff. That negative out in front is a reflection over the x-axis. That causes the thing to open downward. So this particular function is its graph is a parabola that looks like this. Since it's opening down, what's the range? -infinity to -3. We got this part from this, right? That it's opening downward rather than up. And then the boundary, the cutoff of the thing is at -3 because that's where the vertex is. So does this have a maximum or a minimum value? Maximum. There it is, -3. So if I use this function to model something, it goes no higher than -3. That would be the maximum value. Okay, what about rewriting it in standard form? I want to go from a thing that looks like this to a thing that looks like that. So what do? Yeah, we just start simplifying things, right? X minus 2 squared minus 3. So if I'm going to use algebra to expand this thing, where should we start? There are parentheses. I can't really do anything inside them with x minus 2 because those aren't like terms. They don't combine. But then what? There's an exponent, right? The square. So what's x minus 2 squared? X squared minus 4x plus 4 minus 3. Now we can distribute. So there's the equivalent function in this standard form thing where we're just writing in descending order. Now, again, it's the same function. That means it's got all the same stuff, right? The vertex, the axis of symmetry, the domain, the range, the fact that it's opening down, all of that stuff is the same because I didn't change anything except for how I'm writing it. Looking at this, I don't really need a point stick here. Looking at this, what can we see about this function that's obvious, that jumps out at us? Think about all the stuff that we just talked about to, find the stuff that we found. There's only one thing that I can really see looking at this. Do I see 2 or -3 show up anywhere? No. Okay, so I can't just look at it and read off the vertex, right? Okay. Axis of symmetry, again, I didn't see 2 show up anywhere. Domain, I know that quadratics are defined everywhere, so that I guess. But the one other thing that we talked about is the fact that this opens down. How can I tell that from here? That negative out in front of the whole thing. So just like with slope of lines, right? Positive slope means going up, negative slope means going down. Same thing is true here. The leading term, the biggest one, its sign is always going to tell you about the sort of final behavior thing. So since that's negative, that tells me that this thing is opening down. The other information, again, we have to dig a little more to find, right? And there's a formula for finding the vertex if we're going from standard form. Everybody good so far? Okay. All right, well, here's one in standard form, right? Want to do the same stuff. Find the vertex, axis of symmetry, domain, and range. The problem is, as we just saw, here the vertex is just kind of sitting there, right? And as long as I know, what I'm looking for and how to read it, I can just read the vertex off. Here it's not. So how do we find it? Use that vertex formula thing. Okay. So use that vertex formula thing. Find the vertex, find the axis of symmetry, domain, and range. If you already know what completing the square is, then take a shot at it. If not, we'll talk about it in a second here. All right, if what we know is the standard form of a thing, how do we find the vertex? So there's this little formula thingy to give us the x coordinate of the vertex. It's the opposite of b divided by 2a. So whatever a, b, and c are, if I take a and b and stick them into that thing, that'll tell me where the vertex occurs, negative b over 2a. This is like the one time that I can't show you where that comes from because we need calculus to do it. So we'll just take this as kind of a given, like that's a formula, that's a thing to hang on to. Then, because the vertex is a point and I have the function, we just plug that back in. So I'll just write like f of negative b over 2a. But again, really all that we do is take that x coordinate and then plug it back in. So for this one, what are A, B, and C? 1 and 6 and 8. Sign goes with it. They're all positive, but if one of them was negative, you take the sign along with it for A, B, and C. So some room here. The x coordinate of the vertex is negative b over 2a. What's b? 6. What's a? 1. And there's a 2 built in. So the x coordinate of the vertex is negative 3. Oh, okay. All right. That's good. I know. Wasn't even, all that. Come on now. There we go. We're back. Okay. What about the y value? This function was called g, so it's g of negative 3. Okay. Negative 1. Everybody agree? Anybody agree? I don't actually know. I've done it, but not recently. Negative 1. Okay. So the vertex is negative 3, negative 1. What's the axis of symmetry? X equals negative 3. Again, it's a vertical line, so x equals negative 3. Domain and the range. Range, we need the vertex, and we need to know which way the thing opens. Which way does this one open? Up, because the leading term is positive, so it's opening up. So if we had a parabola opening up with vertex at negative 3, negative 1, what's this range? Negative 1 to infinity. Okay. Cool. So there's all the sort of, vital stats. That's the stuff that's on the back of the training card, right? Everybody good with all that? Does anybody have any questions? G is just what the name of this function was. So I'm just plugging negative 3 back in. We got the x value. We plug it back in to get the y value. Okay? Yeah.
Wait, you plug in both.
Yeah, right. Yeah. Replace x with negative 3, and you should get that. Okay. Now, we're going from the sort of vertex form to the standard form. We took the stuff that was already here and we expanded, right? There was a square, so we squared. There was a negative, we distributed. There was some stuff to combine, we combined the stuff. Going the other way, we use a technique that we call completing the square. That's a little like we have to work a little harder to go the other way, because what we're trying to do is take this thing and factor it, but factor it in a really specific way. It's not just factoring, because we want it to look like, where is it? We want it to look like this, right? And be able to sort of read the vertex off. Now, completing the square is a technique that comes up in a bunch of places. I italicized this because it's, think of this like a proper noun, like it's the name of a thing, right? Completing the square is the name of a thing. If you, Google that phrase, you get stuff talking about that specific thing. Here's how we do it. Now, this does factor. If we just do the normal trinomial factoring, look for things that multiply to 8 and add to 6 thing, you can factor it. But again, what we want to do is complete the square. And just for emphasis, I'm actually going to, write that out again, and I don't know, maybe underline it in an exciting color or something to. This is one of those things that on a test question, I'm probably going to say, bold it, like do this specific thing, right? Kind of like the even and odd stuff on the last one. Because it's a technique that, we need later on for other stuff as well. Vertex form, okay. All right. So the vertex form part of this is that our goal is to have this come out as something like this. I don't know what these things are yet, but I want to factor as a perfect square. That's why this is called completing the square, because we're trying to factor and force it to factor like a perfect square, right? So geometrically, it's to sort of take a rectangle and force it to be a square. That's kind of what's going on. To make this happen, let's think about what happens when you expand a perfect square. So just, unrelated sort of footnote aside thing. If I take x plus 5 and square it, that means multiply it by itself. When you multiply it by itself, what do? Distribute everybody, right? Do the binomial expansion. So like that, x squared plus 5x plus another 5x plus 25, and 5 times 5, right? And then we combine like terms if there are any. Basically, what we're doing here is starting here and working backwards. But after things have been combined, right? So the way we make this work then starts right here. If we're trying to force this to factor like a perfect square, perfect squares mean two of the same factor multiplied together, right? That's this. If you multiply two identical factors together and do this expansion stuff, the part that was the like middle part of the product, the outer and the inner parts, those are identical before we combine them together, right? And that's where this 10x came from, this 5x plus 5x. So the way we make completing the square work then, to again sort of force this kind of factoring, is to start by focusing on this. I'm not doing anything with those, but that's 6x. If I'm going to make this factor like a perfect square, I need to break that up into two pieces, but they need to be the same. So what do you give when you split 6x in half? Okay. I'm just going to space things out a little bit. So what I'm going to do is kind of ignore the 8 for now. So just, push it off to the side and sort of leave some space here. I want to treat those, x squared plus 3x plus 3x, as though they are 3/4 of an expansion like this, right? So basically x squared plus 5x plus 5x. I'm saying it's that part of the expansion. If the first and outer and inner parts of the product look like x squared plus 3x, what's the missing part here? What would the factors have to look like to get this out of expanding them? Sorry. There we go. To expand this and get that, it'd have to be x plus 3, right? X plus 3 times x plus 3. So the first part of the product, x squared plus 3x plus 3x. Okay, x squared plus 3x plus 3x. What would this be? 3 times 3, so 9. So the thing's called completing the square. Here's your square. X plus 3 times itself, that's x plus 3 squared. There's the square. Completing, if we need to complete the square, that means it's missing something, right? It's incomplete to begin with. Here's what we were missing, this plus 9 that I needed to use to factor this. Well, okay. This stuff factors like that, which becomes this. We're missing something though. Right, I've changed things all the way down to saying these things are equal, but here I threw in a plus 9 that wasn't there before. So what do? I can't just have that extra 9 in there without changing, whether these things are equal or not. If I add 9 here, where does it come from? That's the same y all along, right? Okay, well, if I'm going to add 9 right here to be able to use it to factor this stuff to get that perfect square, one way to do that would be to add 9 to the other side also, right? You can do something to one side of an equation as long as you do it to both. Plus 9. But since we're talking about a function and rewriting a function, we kind of want to keep everything on one side of the equation. So the usual thing is to move that over to the other side. So now everything is still like balanced, right? It's all still the same. Y equals this stuff. Okay, well then y plus 9 equals this stuff plus 9. Okay, well then y equals this stuff minus 9 because I moved it over. So what's left over on the outside? 8 minus 9 minus 1. What was the vertex for this function? -3, -1. Oh, hey, look. -3, -1. This is it's a technique, right? Generally, any math technique is a thing that the first time you see it looks like a trick, and it kind of is. We do it because it works. It's one of those kind of things. But then repeating it, okay, now it's not a trick anymore. It's a method. It's a technique, right? It's a tool I can use. So this is a thing that probably, however you talk about it the first time you see it, you're gonna be like, that feels like, a lot. Like this middle step seems kind of weird. Why do we do that? But then you do it a couple of times and things start to click, right? So let's do one more. X squared plus 4x plus 1. Again, if the thing we want to do is complete the square, our leverage, our end of the problem is always going to be this middle term. That's always the thing that we look at. If you look at, if you want the like textbook sort of, formulaic version of this, it'll say something like take b and divide b by 2 and then square b over 2, and that's the thing that's missing. And that's the same thing I'm doing. I'm just not talking about it that way. But this is our end. For this to factor like a perfect square, I have to break that into 2 equal pieces, which would be what? 2x. Okay. Hang on to this plus 1 for a second. X squared plus 2x plus 2x. If you got those from expanding something, what would the factors have looked like? X plus 2. That's the only way to get plus 2x and plus 2x. So x squared in the lead term, so x times x, right? If we're breaking it up evenly, that's the only way to break x squared up evenly, x times x. Okay, well, if that's x and that's x, let me even fill these in, one at a time then, thinking about it that way. Okay, I want to get x squared from the first part of the product, and I want these to be identical. It's got to be x times x. Okay, Then I want the outer part of the product to be plus 2x. I've already got x here as like part of the outer part of the product, right? When these things hit. If I want plus 2x, then this has to be plus 2. Okay. The inner part of the product, I want to be plus 2 times x. I've got an x sitting here in, half of the inner part of the product. So this needs to be plus 2 as well. Okay, well, that's good because I wanted these to be identical because I'm trying to force this perfect square factoring thing to happen, right? That's good. That's x plus 2 squared. Cool. That's what I wanted, right? That sort of thing. We've covered the first part, the outer part, the inner part. What's left is the last part of that product here, which would be 4. Okay, that's the completing part, right? That's what was missing, that plus 4. It's got to come from somewhere though. So either add it to both sides and then move it over, or if you want to just work on one side of the equation, which is what I usually do, plus 4 minus 4, because those cancel, that's 0, they offset, so I'm not changing things, right? This one I use as part of this factoring. This one is left over on the outside, and I compare it with combine it with the stuff that's left over. So 1 minus 4, -3.
I don't know if this would only be a detriment, but when you do the 2 times 2 to get the plus 4, can you just go ahead and swap the sign? Like that'd be, would that screw me over later?
You're talking here?
Yeah, instead of
Yeah.
doing all that,
Uh-huh.
I'd be like, hey, that's -4, okay.
Right, yeah. Yeah. And again, I know that like, as I'm talking through this, I'm kind of like jumping around, right? Like, and we're not used to that. We're used to sort of step by step working like down the page, right? And here we're kind of going, okay, this does this, so this happens, and I'm kind of jumping back and forth a little bit. That's to talk you through where these things are coming from. Again, once you do a few on your own, hopefully you'll start to see and like anticipate how some of those things are gonna go, right? Okay. That's completing the square. Here's one more place to try that. So again, find the vertex, find the axis of symmetry, domain and range, and then try completing the square on this one. Y'all take a few minutes, talk to each other. We'll look at it together in a second. you have the function, so if you get the X value, you want the Y to go with it. All right, what's the vertex? -1, -18. Axis of symmetry. Let's see, plug -1 in. 2 times, so, plug -1 in. So -1 squared is 1 times 2 is 2. 4 times -1 would be -4. So 2 minus 4 minus 16. Yeah, -18. Yeah, no, I mean, yeah, it's arithmetic stuff, so you can go wrong but yeah, it's -18. Domain range -18 to infinity because this opens which way? Up. How do we know that? Because the leading term is positive. So it's opening up. Okay. All right. What about completing the square for this? What's different about this one than the others that we looked at? There's that leading coefficient of 2. Okay. How can we deal with that? We could hold that 2 out of the whole thing. I could factor it out. You could divide it to the other side if you want, as long as you remember that later you're going to multiply it back over. That's fine. But think about graphically like what that 2 does and why it doesn't just go away. What's that 2 going to do to this parabola?
It's vertically.
It's going to stretch it vertically, so it's going to be, sort of taller and skinnier than if everything was x squared minus 2x minus 8. These are going to sit in the same place, ignoring that 2, they're going to have the same vertex and stuff. But that 2 is going to stretch the thing out. So it's important that it not just disappear. You could write this as y over 2 and then work on this and then multiply the 2 back over, that would work too. Okay, so I'm just gonna hang on to the 2 there. Actually, I don't know, maybe not. Do you guys like the idea of dividing both sides by 2 first and then bringing it back over later? Okay, let's try that. And so that I don't forget about it, I'm gonna write it in, the flashiest of colors, that's y over 2. And then I'm gonna do all my completing the square stuff on the right-hand side. Middle term is negative 2x. Dividing that into 2, splitting that in half would be negative 1x twice, right? Negative 2 divided by 2 is negative 1. So there you go. That's breaking that in half. And then again, if I'm sort of thinking of that as, 3/4 of a binomial expansion, what would the factors have to look like, and what are we missing to put the ol in FOIL? One times one, yeah. The factors would have to be. Yep. Oh, yeah, sorry, it should be +2. Sorry. Man, y'all speak up sooner. I got 2. I divided 2 out of everything here. These were all even. There's a factor of 2 sitting out in front. So divide the whole thing by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. And 16 divided by 2 is 8.
Why'd you share?
Because y'all said you wanted to divide the 2 over to the other side of the equation. Uh-huh. Yeah, hang on. We'll finish this. Yeah.
Wait.
Yep.
What if it the same answer if I didn't divide it by 2?
Yeah. Hang on. I'll run it out the other way in a second. Okay. So +1. Y'all want to make a big deal about being correct. The factors would look like x plus 1 and x plus 1, right? So squaring then the missing part +1. So subtract 1 to correct for that. This stuff is what's getting factored, which means there's a -9 sitting outside. Okay, but all along, this was y over 2, which isn't going to fit because I wrote it too big. So to get y, we got to multiply the whole thing by 2. 2x plus 1 squared minus 18. Now, if you don't want to do that y over 2 thing, you can just factor the 2 out and hang on to it. Again, break this up so it's x squared plus 1x plus 1x. Which again gives us +1 here, but then there's this -8. This part is x plus 1 squared. This is -9. And then to drop this big set of parentheses, distribute that 2, and we get to the same place.
Is that more confusing?
I don't know. You tell me. It's up to you. So if you hang on to the 2 here, I mean, the only difference is, whether we keep it on the right-hand side, hang on to it that way and deal with it, which means later, carrying through that it's not really 9, it's really 2 times 9, or move it over to the left and get it out of the way, and then bring it back if you know. right? It's just two ways of dealing with that too. Okay, go home and try a few, because again, this isn't really gonna click until you try to do it on your own. So go home, try a few, I'll see y'all tomorrow. Again?